In this video, we're going to introduce locating real zeros of polynomial functions. So, let's suppose that f of x is a polynomial. The important things of this polynomial that we're going to worry about for the result that we're going to talk about as the rational root theorem are going to be the leading coefficient, the a sub n, and the constant, a sub 0. So what the rational root theorem says that if you have a rational root, or a rational zero, of f of x, now remember rational zero means a rational number means a number that can be written as a fraction, so p over q, then any of the rational roots of f of x have to be of the form p over q, where p is a factor of the constant term of the a sub 0, and q is a factor of the leading coefficient, the a sub n. So let's look at an example illustrating what the theorem actually says and what it does not say. So let's see if we can write out the potential rational roots of the polynomial f of x equals 9x to the fifth minus 15x to the fourth minus 25x cubed plus 13x squared minus 3x minus 14. So first we look at our factors of our constant term and our leading coefficient term. So our constant is 14. The factors of 14 are 1, 2, 7, and 14. We could do plus or minus either of those as well. So that's why we're going to list it as a set form and then put a plus or minus out in front. We could list it out as plus or minus 1, plus or minus 2, and so on. Just a little bit more convenient to notate it this way. And then the factors of the leading coefficient, well, the leading coefficient is 9. The factors of 9 are 1, 3, and 9, so we get plus or minus the 1, 3, or 9. So now if we're going to make our list of potential rational zeros, we remember these are going to be our possible numerators, these will be our possible denominators. So we can do 1 over 1, 2 over 1, 7 over 1, 14 over 1. 1 over 3, 2 over 3, 7 over 3, 14 over 3. 1 over 9, 2 over 9, 7 over 9, 14 over 9. So each of these possible numbers here are your numerators. Each of these possible numbers here are your denominators. So we've got, 12 numbers in this list, and we can do plus or minus any of them. So we get a possibility of 24 different rational roots. Now, be very, very, very careful. The theorem does not say that these have to be the zeros of the polynomial. In fact, what we'll talk about in a later video is that that list of 24 would be way too many zeros for that particular polynomial. Okay, but it does say that if the polynomial has a rational root, if there's a fraction that makes the polynomial 0, then it has to be one of those in our list. But of course, it's also entirely possible that you don't get any rational roots at all. For example, if I look at the zeros of f of x equals x squared minus 6, the roots here are plus or minus root 6. You can see that pretty easily. However, root 6 is not a rational number. And if we went through making up our list of possible rational roots, the constant term is a 6, the leading coefficient is a 1, so you could do 1 over 1, 2 over 1, 3 over 1, 6 over 1, factors of 6 over factors of 1, to get out of the possible, the list of rational roots are these, but it turns out that none of them actually even worked. Alright, so let's see if we can put this rational root theorem into practice for us to be able to solve the problem. Let's say we're being asked to find all the zeros of the polynomial f of x equals 3x cubed plus x squared minus 4x minus 10. The first step will be to find the factors of your constant and find the factors of the leading coefficient. Factors of 10 are 1, 2, 5, or 10, so we could use the positive of any of those or the negative of any of those. And the factors of 3 are 1 and 3. So now we make our possible fractions. We can do 1, 2, 5, and 10 all over the 1, or the 1, 2, 5, and 10 all over the 3. So we get those 8 possible rational numbers, and then we add in the plus and minus, because we can do either the positives or the negatives. So we have 16 potential rational roots. We could test all of these. That would get very, very tedious. So if we do, instead of doing that, what we'll do is we'll start with a graph of the function, use a graphing utility to help us out, and then decide which ones are likely. Okay, so here is a graph from a graphing utility of what this function looks like. I see that the function crosses the x-axis somewhere between 1 and 2. Well, if I look at my list of numbers, there's only one number that's between 1 and 2, and that's 5/3. So our guess would be that 5/3 is a root, but we need to check. The way we'll check is, of course, use synthetic division. So using synthetic division, if I use 5/3 as my root and put my coefficients of the polynomials in the top row, bring down the 3, multiply by the 5/3, add to get the 6, multiply by the 5/3 gives you 10, add to get the 6, multiply by 5/3 again gives you 10, add to get 0. So I really do see that 5/3 is really a 0. So that tells us, of course, that the quotient of the original polynomial, 3x cubed plus x, that should be an x squared, there's a typo there, that should be an x squared, minus 4x minus 10 over x minus 5/3 is the polynomial 3x squared plus 6x plus 6. Well, now that we have it down to a quadratic, we're essentially done with the problem because we know how to solve any quadratic equation. We can either try to factor it, but even if it doesn't factor, we can always use the quadratic formula. So in preparation for using the quadratic formula here, let's divide both sides by 3 since those 3 coefficients of that polynomial have a common factor of 3. Leaves us with x squared plus 2x plus 2 equals 0. So we get negative 2 plus or minus 2 squared minus 4 times 1 times 2 all over 2 times 1. So we get negative 2 plus or minus a square root of negative 4 over 2. Square root of negative 4 is the same thing as 2i. So we get negative 2 plus or minus 2i, or if we factor out a 2 and cancel, we get plus or minus, or excuse me, negative 1 plus or minus I. So we get 3 zeros here. The 3 zeros are 5/3, negative 1 plus I, and negative 1 minus I. So again, one of the things that we use the rational root theorem is to give us a list of potential rational roots to knock down the power. Once we get down to a quadratic, we're able to solve any quadratic using essentially a quadratic formula if we have to. All right. So going on to another property of polynomials. Polynomials are very, very nice functions. There's lots of different things that are nice about it. We know that no matter what number we choose, we can always plug it into a polynomial. And then there's lots and lots and lots and lots of nice properties that polynomials have. We will study polynomials not only throughout this course, but subsequent courses in mathematics. One of the nice features that polynomials has is if you graph the functions, if you try to draw their graph, then you can do it without lifting your pencil. There are no holes, no breaks in the graph at all. So we refer to these types of functions as continuous functions. Continuous functions have a special property that is known as the intermediate value property. And we'll see what the intermediate value property is in the statement of the following theorem, which is called the intermediate value theorem. So there's going to be a lot of math symbols here. We're going to break this thing down and talk about what each of these symbols mean. So the theorem says that we're going to let f of x be a continuous function. What we're going to be interested in for our purposes in this chapter are polynomials. And let's just consider the interval from a to b. Then if k is some output between f of a and f of b, then somewhere in between we have to have an input that has the k as the output. So let's look at a picture. Here is a polynomial, so it's continuous. Here we have f of a. Here we have f of b. So my output f of a here is here on the y-axis. My output f of b is here on the y-axis. So I just choose some number k in between those two values. Well, if I just go across over to the function to where I hit the output here at k, I can drop down then to the x-axis and see the input that I need to give me that value of k out. So basically, another way to say this is that if I want to get from this low height to this high height, I have to hit every height in between. That's another way to say the intermediate value theorem. If I want to go from low to high, or you can flip it around from high to low, it doesn't matter. I have to hit everything in between if I'm not allowed to pick my pencil up when I'm drawing it. So the only thing we're going to use intermediate value theorem for our purposes is to figure out an interval where a 0 might be. So in particular, notice the way I've drawn this function. Notice that f of a is below the x-axis and f of b is above the x-axis. So the function had to cross the x-axis somewhere in between. That's how we're going to use the intermediate value theorem. So let's show that the polynomial f of x equals x to the fourth minus 5x squared minus 8x plus 13 has a 0 between x equal to 1 and x equal to 2. So we're going to plug in 1 and 2 into the function. When we plug in 1, we get out 1. When we plug in 2, we get out negative 7. So when we're at x equal to 1, the function's above the x-axis. When we're at x equal to 2, we're below the x-axis. So what that says is that we've got the point 1, 1 above the x-axis. We've got the point 2, negative 7, which is below the x-axis. So somewhere in between, the function had to cross the x-axis. Okay? So here we are above the x-axis, here we are below the x-axis, and sure enough, if I go from this point to this point, by connecting the dots, I have to hit this line. I have to hit the x-axis. So in particular, that tells us that the function has to have a 0 in the interval from 1 to 2.